For Unit 5 Notes Part 4, we're going to talk about the VSEPR model, or the valence shell electron pair repulsion model. Basically, all we're going to do is we're going to continue to draw out the molecules the exact same way that you've been doing. But now what we're going to do is actually put the geometric shape with that and give that shape a name. This is all based on the fact that electrons want to be as far away from each other as possible. So whether that electron pair be a bonding pair, which is just a single bond, or every bond in a double or triple bond is one pair of electrons, or a lone pair that focuses as a pair of electrons. Now, for a double or triple bond, the entire bond counts as one pair of electrons. So even if it's a triple bond, there's technically 3 pairs of electrons. For the shape-wise, it only counts as 1. So we're just going to follow a real quick 4-step process here. We're going to write the electron dot formula exactly like we've been doing. We need to determine the number of electron pairs around the central atom. So all that means is how many bonding pairs, how many lone pairs. And then we're going to determine the arrangement and the molecular geometry. And we have a shapes reference sheet that we're going to go to. I will click over to that when we start drawing these out and we're looking for our answers. And you should have a copy with you as well. For the arrangements, in general, if there are 2 electrons pairs around the central atom, it's going to end up linear. The bond angles are going to be 180 degrees because that means they are as far apart as possible. Remember, we're just working in a 360-degree circle, but I shouldn't say circle, I should say sphere, because we are in 3 dimensions. If there's 3 pairs, we're going to end up in trigonal planar, 120-degree bond angles. Tetrahedral, 109.5. Again, we're going in in 3 dimensions, so there'll be one kind of coming out towards you and another thing's going backwards. Trigonal bipyramidal have 90 and 120-degree angles, so you're going to see what that looks like. And the octahedral has all 90-degree angles between each one. Lone pairs tend to take up more room than a bonding pair, so usually you'll see a kind of a question like, what would you expect the bond angles to be? If there's a lone pair there, you expect them to take up a little bit more, so the bond angles tend to shrink a little bit. So like something like a trigonal planar, if one of the things coming off the central atom is a lone pair, it'll take up a little bit more room, so the bond angle between the other 2 pairs would be less than 120. So let's do this. We're going to draw out the molecular geometry of SiF4, and we'll do that one first. So Si, we're just going to follow our same rules. Oops. Si has 4 valence electrons. Fluorine has 7 times 4, which is 28. So we have 32. We put silicon in the middle. We put a fluorine up here. We put a fluorine right here. We put a fluorine right here. Nothing has changed. There's our skeleton structure. So we've used 8. So there's 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So now our central atom has 8 around it. Each of our outside atoms has 8 around it. So there's our thing. So now what we're going to do is we're going to go over to our shape sheet, which looks like this. And we had, if we look back at our atom, we have 4 bonds around our central atom. So 4 bonding pairs and 0 lone pairs. So if we look here, 4 bonding pairs, 0 lone pairs. Our molecular geometry, or our shape, is tetrahedral. So all we need to do then is add on there for this is just say this is a tetrahedral. A tetrahedral is just a 4-sided figure in 3 dimensions. For water, hydrogen has 1 valence electron times 2, so 2. Oxygen has 6, so we need 8 total. Water looks like this. Remember, each H only needs 2. And I know what the shape looks like a little bit, so it helps me draw that out. So oxygen has 2 bonding pairs and 2 lone pairs off of it. So again, we're going to go back to our sheet. The nice part is, if you look over here on this left side, it says total electron pairs. So we know there are 4 because there's 2 bonding and 2 lone pairs. So we know to look in this section. 2 bonding, 2 lone pairs. Our shape is bent. So we can write that down for water. ClO3 minus, chlorine has 7, oxygen has 6 times 3 is 18, and we add 1 more because it's a negative, so we have 26 to work with. So again, you put chlorine, oxygen, oxygen, oxygen. So we've used 6, so there's 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So if we're looking at this, we have 1, 2, 3 bonds and a lone pair. So again, we have 4 pairs of electrons coming off. So So we know to look in this general area. 3 bonding pairs, 1 lone pair, trigonal pyramidal. So for that one, you can just write trigonal pyramidal. Okay, for the last one, ICL3. All I has 7, CL has 7, so it's 7 times 4, so we have 28. So we put I, CL, CL, CL. We use 6, so 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So we have 3 bonding pairs and 2 lone pairs off of our central atom. So when we go over to our sheet, we got to scroll down a little bit. We had 3 bonding pairs, 2 lone pairs, so that is T-shaped. So we click back there, and we can do T-shape. You can see I drew it out like a T because I knew how we were going to end up with that. So for all of these, you just found the exact same rules for writing things out that you have done before for drawing them out. All you need to do is, once you are done, identify how many bonding pairs and how many lone pairs are around your central atom. Use your shape reference sheet and find that sheet, and find the shape. In the future, you are going to have a general idea of what those shapes are to be able to come up with them. So you might want to get on top of starting to memorize what the different shapes are and how many bonding and lone pairs each one has.